Okay, so within this tutorial we're going to have a look at modifying metals. Now we'll have a look at a technique called alloying. Okay, so alloying is essentially a combination of metal and another element, and this other element may be metallic or maybe non-metallic. Okay, so we'll have a look at examples in a moment, but a common type of alloy is steel. Okay, so steel, which is very important in infrastructure, it's predominantly made up of iron, but it's actually iron and carbon. Okay, so iron is the metallic form, carbon is the non-metal in this case. Okay, and joining them together in a 3D lattice creates the material steel. So steel is the alloy. It's the name of the alloy. Okay. So we have different types of alloys, three major types. The substitutional, interstitial, and a mixture of both substitutional and interstitial. Now, we'll have a look at a picture that describes these types of alloys, and as you can see here, I've just used the example of iron. Okay, so iron is a pure metal. It's the periodic table by itself, and iron as a metal is very soft. Okay, now in pure metal state, you can see just a metallic lattice. Okay, now a substitutional alloy is when the metallic atoms are replaced with another, usually metal, of similar size. So when the original metal atom is replaced with a different metal atom. It's usually metal atom because the metal atoms are similar sizes. So you can see in this figure here, we originally had, let's say, the example I used is copper and zinc. So let's say that this red atom here is copper, so Cu, and say that that's zinc, Zn. So basically it's just when one atom replaces the other. And they're both metals in this case, so that's a substitutional alloy. Now there are different examples, and you do need to know an example for your test. So you might want to remember brass, which is composed of copper and zinc, or another one is bronze. So bronze is actually just a combination of copper and tin. Okay, so those are examples of substitutional alloys. There might be a few more in your textbook, which I recommend looking over. Now, the other one is called the interstitial alloy, and this one is essentially there is no replacement of atoms. As you can see, the metal atoms all still exist and are locked into place. The only difference with an interstitial alloy is that you have a new atom which is found in between the layers of the original metal. So these atoms can be thought as being filling the gaps of the original metal. So an example of that, as I mentioned before, steel. Steel is a material that is made up of iron and carbon. So this would be the iron, and these green dots here are the carbon atoms, and so they actually just fill in between the space of the metal atoms. Okay, so that's an interstitial, when you've got usually a non-metal being combined with the original metal, and that therefore changes the property of the original metal. Okay, so now why do we alloy? Okay, so one of the major reasons why people alloy in industry is to change the original property of the metal. So as I mentioned before, I showed you an example of iron. Now iron as a metal is quite soft, and it would not be appropriate to use in infrastructure. You can't use it in buildings. It's just too soft. It's actually very reactive as well, so quite reactive with the environment, so it would be not great because it would rust straight away. On the other hand, steel is an alloy that's combining iron and carbon. Now steel is a lot stronger as a metal, and it's used, you know, it's pretty immune to rusting as well, which is really good in the building industry, and you know, creating ships and stuff like that. So it's a very good one to use, and you can see that obviously, well, steel is a very strong material, so it's appropriate to use in building. So that's how we change the metal strength, by just adding a particular percentage of carbon into this particular matrix, into this particular lattice, and that changed the metal strength. Differences occur in electrical conductivity within alloys. So actually comparing iron to steel, iron can conduct electricity up to 17% efficient, whereas steel drops to 3 to 5% efficiency. Now, you can think of this drop as a result of, you know, all the delocalized electrons in iron that are here, they don't have much resistance. They can move. So you conduct electricity, they just move across. Whereas in this interstitial alloy, those electrons, when they're floating around in this particular matrix, now suddenly they have these carbon atoms blocking them. So the electrical conductivity probably will get affected by interstitial alloying. They could be affected also by substitutional alloying, but probably not to the same extent as interstitial. Now there's also so sometimes, actually back to this, sometimes we do want differences in electrical conductivity. Sometimes maybe it's appropriate to lower the electrical conductivity of a metal. Okay, so you may not always want to have high electrical conductivity. That may not be a benefit. Sometimes you may want to reduce that as well as heat transfer. It may be appropriate to prevent heat transfer. If you imagine, like in building, by doing that you would prevent, in the case of a fire, you would actually prevent heat being transferred down the building as fast down across the metal. So that might be a benefit. Differences in malleability and ductility. So iron, being a soft metal, is quite malleable, whereas steel is not as malleable. It cannot be shaped that easily into all kinds of configuration. Ductility, the ability for a metal to be put into a wire format. In the case of when we alloy, sometimes it's harder to turn the metal from its pure form into, if you take the pure form of a metal, sometimes it's easier to put it into a wire, and when you alloy it, it might be harder to put into a wire format. However, sometimes alloying may also create a particular positive characteristic, such as being more resistant to rust, for example. So alloying can cause differences in malleability and ductility, and in industry, depending on where the use of this particular metal is, that might be appropriate. So we may alloy in order to change these configurations. There also might be differences in melting temperatures. So sometimes we want higher metals to have higher melting temperatures, sometimes we want them to have lower melting temperatures. It again depends on where you use this in the industry. So those might be some of the reasons why we tend to alloy. So lastly, I forgot to mention the mixture of substitutional and interstitial alloying. So this one is just basically when you have both. Okay, so a scenario when you have both interstitial alloying and substitutional alloying. That's also a possibility. Now, one of the actual examples of that is stainless steel. So this stainless steel actually has iron predominantly in it, mixed with usually chromium or nickel. Just right, chromium or nickel. So chromium and nickel are both metals. Okay, so that would be an example of substitutional alloying. And then also carbon. Okay, so stainless steel, very important in cooking. A lot of utensils are using stainless steel, and this is the combination. So the chromium and nickel would be an example of substitutional alloying, and the carbon would be the interstitial. So this is a mix of both. Mix of substitutional and interstitial. Okay, so quite an important example as well. You may want to remember this one. Okay, so hopefully that explains what an alloy is, the different types of alloying. Make sure you also have an example of an alloy. So steel, brass, bronze, and then stainless steel, and then knowing how alloying changes or can alter the physical properties of that metal.